Hi everybody and welcome back to lesson 19 of the Dead Earth game development series brought to you by the Game Institute. I'm Gary Simmons, and before we carry straight on in this lesson, I just want to draw your attention to a bit of a mistake, putting it mildly, that I made at the end of the last lesson. Now, if you've downloaded the code from the resources section, don't worry, the code was always correct there. But basically, I noticed the mistake that I'd made after I'd uploaded the video, but before I deployed the resources. So all of the scripts in the resources system are sort of up to date and free of this bug. So just to remind you, you'll remember that at the end of the last lesson, we were implementing our AI zombie state class derived from AI state. And you'll remember that this is the class that's going to provide some of the base functionality that all of the child zombie states are going to use, things such as patrol, idle, attack, etc. Now, you'll also remember that we were in the middle of writing our onTrigger event function, which is called by the parent state machine whenever there's an event that needs to be dealt with. And all we've done so far, really, is just implemented the code here that dealt with the case where the collider that raised the event was on the player layer. So, in other words, if the player had entered the zombie's sensor trigger. And you'll remember that in this case we check if the collider is visible, and if it is, then we set this as the new visual threat that the child states that we're going to write later can then assess and see if it wants to make that the new target. Now, this function used the collider is visible function, which we also wrote in the last lesson, and that's where my error crept in, really, because you'll remember that the first half of this function basically tests that the collider that raised the event is within the zombie's field of view, and if it's not, then it returns false. However, the second part of the function performs a raycast to test that the collider that raised the event has line of sight with the zombie, and we do that by performing a raycast, and if any other collider sort of gets in the way of that ray and is closer to the zombie, then that may be blocking the threat. So it could be that it's the player that's entered the sensor trigger, but he's behind a building or whatever. One of the things that we had to test was that if the game object that is blocking line of sight is on the body part layer, and remember we said later on we're going to create ragdolls from our zombies, and that means that every body part of the zombie is going to have a collider on it. Then we need to make sure that if it's one of the zombie's body parts which is blocking our line of sight, then it's not one of our own body parts. We don't want the zombie ruling out a threat because its own arm in the middle of an animation or whatever is blocking its line of sight. So you'll notice that to do that, I just get the layer of the collider that we're testing, and if it's on the body part layer, then I know it's a body part, and we test that it's not our body part. However, this is where the error is, because obviously the layer property of the game object is the numerical index of the layer in the layers list here. We pull down the layers drop down, and what I did right up in the start function, the awake function, I just did a kind of copy and paste of the line up above, which was using the layer mask class's get mask function, which of course is incorrect. We don't want a mask here, we just want to know what the numerical index of the AI body part layer is. So when we calculate that, instead of using the layer mask class's get mask function, we use the name to layer function, where we pass it the name, just a string, of the layer that we wish to get the numerical index of, and it will return that integer index, which we then store in the body part layer, and our code has now been fixed. Now, the next thing I want to do is I just want to do a slight bit of refactoring, because something dawned on me at the end of the last lesson after I posted the video. So I just want to jiggle things around a little bit and make things work slightly differently. If we go down to the collider's visible function, you are reminded that one of the things we did at the top of the function is we had to cast our state machine variable, which remember is a member of the base class, and although it points to our zombie state machine, it's only of type AI state machine, not of type AI zombie state machine. And this code in particular, and of course many of the other functions that we're going to write in derived classes, are going to want access to the properties of the zombie state machine, not just the state machine. So what we have to do is first of all check that our state machine is actually of the correct type, that it is of type AI zombie state machine. And if it was, then what we did is we cast it and stored it in a local variable of its actual derived type. Now, it dawned on me that we're going to have to do this a lot, because pretty much all of the child states that we're going to derive from this class are all going to want access to the extended properties of the AI zombie state machine. So what I'm going to do is I'm going to sort of trap this at the kind of the startup process. So if we go back to our AI state class from which AI zombie state is derived, you'll remember that we had this set state machine function, and this function is called by the state machine for each of its child states in its startup function. So basically it fetches all of the states that are on its game object and calls this function, passing itself in as the parameter, so that all of our states have a reference to the state machine as its base type, AI state machine. So what I'm going to do is I'm going to make this a virtual function so that we can override it in the derived class, and then in the derived class we can of course call this function to make sure that the base class variable gets set correctly. But we can also do that cast in the derived class's set state machine function, store an additional reference to it in the derived class as its correct type, AI zombie state machine, and then any code that wishes to access the zombie state machine can then just do that by using that class variable. So I'm going to save that off, having made it a virtual function, and then what I'm going to do is I'm going to just copy and paste that a little bit, save myself a bit of typing in the AI zombie state class, and then if I go back to the AI zombie state class underneath the awake function, I'm going to paste that in there like that, make a function out of it, and I'm going to change virtual to override. So we're going to override this function, and the first thing we're going to do then in this function is we're going to do that little safety check which says if this function's been called, then really we only want to store a reference to this state machine if it is of the correct type, AI zombie state machine. So I'm going to say if state machine, which remember is what's been passed to us as type AI state machine, get type equals, then I'm going to check that it is of type AI zombie state machine. Well, then we know that everything is working right, the game object has been configured correctly. So in that particular case what we'll do is we will call the base class version of the function, passing in the state machine reference that we've been passed. But then what we'll also do is in our new zombie state machine member, we will cast that state machine to its correct type, like so. So of course what we need to do now is we need to create this new class member. So I'm going to go up to the top of the function, I'm going to create a new protected variable of type AI zombie state machine. I'm going to call this zombie state machine as we've just seen, and I'll set it to null by default, and of course that will then be set by the parent state machine. And of course if for whatever reason we've set our objects up wrong and we've added a load of zombie states to a game object that doesn't have a zombie state machine, it just has some other type of state machine, then this will fail and none of those references will be set. So state machine and zombie state machine will be null, and that's easy to check in all functions. Now if we scroll down to the onTrigger event function, you can see that there are lots of places where we're just referencing the base type that's stored in the base class, and there's no problem with that, because wherever we're using that, we're just accessing properties that are available in the base class as well. But I think to be consistent, whenever we're in the AI zombie state class or any of its derived classes, whenever we talk to the state machine, we should probably just talk to it for consistency using its correct type. So I'm going to change all references to state machine to zombie state machine, because I just think it makes it more consistent. And if we come back to this in a few months time and we see sometimes we're accessing it as zombie state machine, sometimes we're accessing it as just state machine, well, I know what my memory's like, and that, my friends, is going to confuse me greatly. And it doesn't take a lot, especially at my age now, to confuse me. Literally just tying my shoelaces can have that effect. Okay, so I changed it here. If you're following along, I changed it here, I changed it here, and I changed it here, and I changed it here. And if we go down to the collider as visible function now, we can get rid of that whole checking the type and casting it to the correct type, because we already have it as the correct type in our zombie state machine member. So I'll delete that code, and then I'll change, just like I did in the other functions, anywhere where it references state machine to zombie state machine. Here I need to change that, of course, where we're using that local variable which no longer exists, zombie state machine, like so. I need to also upgrade this to zombie state machine here, where we're just getting the radius of the sensor trigger. And here I need to change zombie machine to zombie state machine. I think that might be it. Now there is one case here where I'm using the base type of the state machine rather than zombie state machine, but I'm going to leave that how it is, because in this particular case we're just fetching the reference from the game scene manager's get AI state machine function, which remember is a function that allows us access to that dictionary where we've stored all of the state machines as their base type in a dictionary with all of the colliders that belong to them. So we could change this to zombie state machine, but then we'd have to perform a cast here to cast it back to the correct type. So I'm just going to leave that as a state machine here. Okay, so there you go. That's all upgraded. Sorry for that slight detour, but you know, one of the things of this whole series is I'm kind of making this up as I go along. So you're getting a true insight into the development process and how I'm going to change my mind lots of times, probably between videos. And that's good. That's just showing you the thought process that was involved. So if I go back to Unity now, I have an error. Oh, I forgot to say return false. I'm sure you spotted that before me. Okay, now we should be in business. And there you go. So I'm now going to go back to our AI zombie state class and our on trigger event function, and we're going to add some code to deal with some of the other types of threat, because at the moment all we've dealt with is when the threat is on the player layer. In other words, if the player's collider has entered the sensor trigger. Now the next thing I think I'm going to handle is the player's flashlight. Now the way that the flashlight is going to work in this game, I'm just going to create some temporary game objects in the scene, because obviously we haven't created our player yet. So I think what I'm going to do is I'm going to go to the game object menu and I'm going to create a new 3D object, and I'm going to create a capsule, and just holding Control and Shift so it snaps to the floor. I'm going to kind of bring that up. So let's pretend that this capsule is our player's collider, okay? And then what I'm going to do is I'm going to create a child game object of that of type cube. What I'm after here is actually a box collider. And what we're going to do is we're going to create the flashlight's influence as a box collider. Now, I know what you're thinking. In reality, the light that is sort of cast out from a torchlight would be more correctly modeled as a cone or something like that, and you can certainly do it that way if you want. You could go into 3ds Max, you could create a very low tessellated cone, bring that in, create a mesh collider for it, and then just remove the mesh renderer, and then you're just left with a cone shaped collider. However, I think a box collider is going to be just fine for the flashlight's trigger area, because the way I see it, it's kind of the light is going to be much more potent sort of in the center anyway. So we're just basically saying that if we imagine it was a cone, just the light where it's most intense down the center shaft of where the light is facing is going to really aggravate a zombie. So the idea being is if I just alter the box collider, and if the box collider has some kind of length, let's say like that, and then we'll offset its center position so it's kind of starts at the player's position like that, okay? And then obviously what we're doing is as the player's walking around the level with his flashlight, the flashlight is shining, and if at any point, where's Zombie Jill gone? Oh, there she is. There she is. Hang on, let me just turn it around. And if at any point Zombie Jill could be like feeding or something like that, and then we walk up, we don't know she's there, she's on the floor feeding, and then we shine our flashlight in her direction, and we're close enough such that Zombie Jill falls within this trigger, well then what we want Zombie Jill to do is react to it. Now the reason why I mention this is because at the moment we've talked very much about threat assessment being done solely based on the sensor trigger. And the sensor trigger, if we open up Zombie Jill's, such a mouthful to say, I'm just going to call it Zombie Jill from that one. So if we open up Zombie Jill's hierarchy, we can see that under the AI entity game object, we have her sensor trigger, which we're now very familiar with, and we know that that is on the AI trigger layer. And we know that things like visual and audio threats are the only things that are sensitive to this layer. We also know that on the sensor object itself, we have this AI sensor script, and it's actually this sort of child script that traps the on-trigger enter, on-trigger stay, on-trigger exit event handlers, and then deals with passing that information as a threat onto the on-trigger event function of the parent state machine. And we also know that then the state machine really just passes this down into our AI zombie state, whatever state that may be. So it's very much a push system. Other colliders are pushing these threats into the state machine. It's pretty flexible because it means that in the case of the flashlight, for example, we don't really want to handle threats in the same way or have the flashlight trigger on the same layer. We wouldn't want the zombie to become alert when the player's flashlight trigger intersects the sensor trigger. we want the flashlight trigger to actually be sensitive to Gears Capsual Collider, what we call the AI entity. And we also know that Gears Capsual Collider is on the AI entity layer, this one here. And we also know that any triggers that we wish to raise events when a zombie's body enters it has to be on the AI entity trigger layer, not the AI trigger layer, which is what our sensor trigger is on. So what we're going to do is we're going to put our flashlight trigger on the AI entity trigger layer, and then we're going to have a script on the flashlight itself such that in its on trigger enter function, it's going to be notified obviously when Gears Collider, or the collider of any other zombie, is now intersecting that trigger. And on the flashlight itself, we can then use the game manager's AI state machine database to fetch the state machine, and then we can call that state machine's on trigger event function to push ourselves into the threat assessment queue for analysis. So that's why this system is quite flexible, because any script anywhere can push itself as a potential threat into a state machine's on trigger event function. And that's what we're going to do with the flashlight. And that is why I use tags in the on trigger event function to identify the different types of threat rather than just using layers, because our flashlight trigger, for example, isn't going to be on an audio or visual aggravator layer. It's going to be on the AI entity trigger layer. So pretty much any object, for whatever reason, if it wants to, as long as it gets access to the state machine, can push itself into the kind of the threat assessment queue. The reason I've said this is because we're going to write the code that deals with this now in the AI Zombie State class. So I just wanted to show you very briefly how the flashlight is going to be set up. It's just basic trigger interactions. And of course, it goes without saying that we're going to want this trigger to be roughly the right size, such that when we do set up the parameters for the actual flashlight, the actual light source, that it roughly marries up with where we think the light is most intense. So one of the things we need to make sure we do is handle any measurement of distance into this box collider using much the same method that we did with the sensor trigger, because we're going to use the Z size as a means of expressing, if you like, the length of the flashlight's trigger. Now we know that when we change, if I set the Z offset to 0 for the time being of our box collider, we can see that the game object's transform is in the center of the object. So if we make the thing bigger, like say, I don't know, let's say we make it 10 units long, and then move the origin back to where the player is, then really we're only using half of the flashlight, and half of the flashlight goes behind the player. So what we want to do is then just offset it on the Z, so that the origin of the game object, if you like, is at the sort of bottom face of our trigger. Okay, so we're going to need to make sure that when we're doing distance checks that we use that lossy scale procedure that we did before, so that if any of the transforms, either its direct transform or the scale of any transforms in the hierarchy, are not just 1, 1, 1, then we need to apply that scale down to the size so that we get the world space size and the world space position of where this trigger begins. So hopefully that makes sense. So the next thing I'm going to do is create a new tag that we can use to identify the player's flashlight collider. The flashlight plays a very important part of the game, so it can have its own tag. Now, other lights in the level, if we want the zombie to be sensitive to it, such as if the player turns a light on in a room, we could just put that on the visual aggravator layer and just have the zombie react to it when the light goes on if it's within its sensor trigger. But the flashlight is very specifically for, when it's dark, the player's walking around the corridor, goes around a corner, doesn't know a zombie's on the floor feeding, and accidentally shines the torch on it and thinks, oh no, and the zombie gets up and starts trying to figure out what's going on and pursue the player. So we're going to say add tag, click the plus sign, and I'm going to call this flashlight. It's probably one word actually, but don't worry about it. I'll just leave it as 2 words, flashlight, capitalized like so. Now, we're not creating the flashlight or the player controller yet. We're going to be doing that pretty soon though, as soon as we finish the zombie system, or at least got a fair way into it. But I put the tag in there already so that the code doesn't complain that it's a non-existent tag. I'm not sure how Unity handles that. Going back to our AI zombie state, like I said, we've got this conditional for the player. Now we need to do an else clause where we're going to check if it's the second most important type of threat, which is the player's flashlight. The zombie sees player as the highest priority, player flashlight as the second highest priority, then it is visual threats, then audio threats, and then food, which although is a visual threat, is a special type of visual threat, which the zombie only goes to if there isn't anything more threatening to it. So in this else clause, we'll say, much like we did above, we will say if other dot compare tag, and then pass in the name of our flashlight tag, like so. And if the current visual threat that we've stored so far isn't of type player, it's really important, because if we've already stored a visual threat in this update, which is a player, then this will always be a higher priority than this flashlight. So we only step into this code if it's a flashlight threat and we haven't already found a more important threat, i.e. the player. So I'll say doesn't equal AI target type visual player, like so. Then we step into this code here where we can assess the threat. So the first thing we're going to do, because we're going to need to get the properties of the flashlight's box collider. So at the moment, my system only works when the flashlight is a box collider, because this bit of code here is going to do a cast of that collider that's been passed into this function to its correct type, the box collider. So very important point here, you need to alter this code if you intend to model the flashlight as any other collider type. So I'll say box collider, and of course the reason I'm doing this is because I need to access properties of the box collider, the box length and its center offset. So I'll say box collider, and I'll call this flashlight trigger equals, and we're just doing a cast of the collider that was passed into this function, other, to the correct type. So obviously if other isn't a box collider, you're going to get real problems here. So what we'll do is we'll calculate the distance to the transform of the game object that contains the box collider. Remember, our box collider is going to be offset, but we've positioned its transform such that it's at the player's position. So we're really calculating the distance from kind of the player's hand, if you like, to the zombie. So we'll call this distance to threat. We'll say equals, and we'll use Unity's vector3.distance function, which we use all the time, and that is going to be zombie state machine dot sensor position, and we want to measure distance between that and the trigger's transform dot position, like so. And then next we want to calculate the world space z extent of the box, how far it protrudes out from the player, and we're going to use that to calculate how much we've penetrated into the light source. So I'm going to say float z size equals, and we need to get the flashlight trigger's z extent. So flashlight trigger dot size dot z. That's why we needed to cast as a box collider, so we could access these properties here. And then we're going to multiply that by the lossy scale of its transform, so that if there have been any scales along the way in its parent hierarchy, they are all factored in, and we don't just get the size that's specified in the inspector, which is like a local size. We get that all of the parent scales integrated into that. So to get that, we get the flashlight triggers transform, and then fetch its lossy scale property, which is a vector3, and we're only interested in the z here, like so. So now we know the distance between the zombie sensor position and the actual flashlight that the player is holding, and we also know the size of the trigger in world space, how far it extends out in the direction the flashlight is pointing. So now if I divide distance to threat by z size, I'm going to get a factor which, providing the zombie is inside the collider, is going to be in a 0 to 1 range, and this is kind of like a normalized distance, where 1 is going to be when the zombie is right at the very outer tip of the flashlight collider, and 0 or close to 0 when he's right close to the player and the flashlight would be really intense on him. So I'll call this aggravation factor equals distance to threat over z size, like so. And then what I'm going to do is I'm going to use this aggravation factor to determine whether the zombie reacts to it, so that all zombies don't react to it the same way. It's going to be very much based on the sight of the zombie. You know, if the zombie doesn't have good sight, then, which we know, by the way, that sight is in the 0 to 1 range. So we can literally say if the aggravation factor is greater than the zombie's sight, then the zombie doesn't react to it, because only if the flashlight is much more intense on that zombie will it react to the flashlight. I think we'll also say as well, given the fact that if a zombie's feeding and the area around the zombie is suddenly illuminated, then I think intelligence plays a part as well. Now we know that our AI zombie state machine also has an intelligence factor, which is once again in the 0 to 1 range. So I think we'll use that in exactly the same way. We'll say that if the aggravation factor is less than the zombie's sight range and it's less than intelligence of the zombie, then it means that it falls within the thresholds of the zombie's capability and the zombie will react to it. But if the aggravation factor is, say, for example, 0.75, but the zombie's eyesight is only 0.5, or if the zombie's intelligence is only 0.5, then we're basically saying that it won't react to this aggravation. So we'll say if aggravation factor is smaller than zombie state machine dot sight, and aggravation factor is smaller than zombie state machine dot intelligence, well then we're going to react to this threat. Actually, I think what I'll do is I'll make that less than or equal to. And of course that's all we have to do now, is just set it as the threat, because we don't have to check if the collider is visible. In fact, the flashlight will very often push itself into the event queue even if it's not visible. Like I said, if you're behind the zombie and you shine a flashlight on its back, it's going to react to it. So we just need to set this now as the new visual threat. So we'll say zombie state machine dot visual threat dot set, like so, and as the target type we will pass in AI target type, and we've already set up one for the light in that enumeration. It's called a visual light. As the collider, of course, we will pass in our flashlight collider that we were passed into this function, and as the position of this threat we will simply just get the transform of that collider and pass in its position, other.transform.position, and we'll also pass in the distance to the threat, like so. Now that, believe it or not, is our flashlight completely handled. So I think I'll just save that off and check I haven't got any errors, because I probably have. Nope, seems a little too good to be true, but yes, I haven't got any errors. So I think the next thing I'm going to do is the code that handles sound emitters, because these are really cool in the game and they allow the player to do all sorts of things strategically. Obviously, if the player is walking over a noisy surface, metal plate, something like that, then it can aggravate the zombie and that can be pretty terrifying. But the player can also use sound emissions to its advantage. It could, for example, go up to a car, bang the car, set off a car alarm, deliberately to draw the zombies out of an alley that he's intending to get to. So he could set off the alarm, then run away from the car, all the zombies go and investigate the sound, leaving his way free. So pretty cool stuff. So we know that sound emitters are literally just going to be triggers that are going to be on the audio aggravator layer. They're nothing more than that. So in our game, when we wish to enable one of these sound emitters, such as when the player fires a shot in his gun or whether he sets off a car alarm, then we're just going to have a script somewhere that just turns on a trigger on the AI aggravator layer of a certain size. And if that trigger intersects any zombie's sensor trigger, well then we know that the sensor trigger is sensitive to it and it's going to register it as a threat. And you're reminded that we've already set up the tag that our sound emitters are going to use. It's called AI sound emitter, and sound emitters are also always assumed to be sphere triggers. Because all we really need for a sound is a radius that describes how far the sound travels. So as long as the sphere trigger and the sensor trigger intersect each other, then there's going to be an event raised. So let's go and add that new conditional clause now where we deal with sound emitters. And of course we're going to, much like we have in the above code cases, we're going to use the other.compare tag, and this time we're going to pass in AI sound emitter. So I'm going to say else if other.compare tag and pass in our string AI sound emitter, which is the tag we created, then we're going to step into this code block where we're going to test that the sound emitter is a viable threat, and if it is the closest sound emitter, then we're going to store that as the most potent audio threat in the parent state machine. So like I said a moment ago, the sound emitters are always assumed to be sphere triggers, and we need that to be the case because we're going to want to fetch the radius of the sound emitter. So once again, just like with the flashlight, very strict rules on what type of triggers are used as sound emitters. So the first thing we'll do is we will take that collider that we've been passed and we will cast it to a sphere collider. You can see I've cached this sphere collider reference in a local variable called sound trigger. Next, if sound trigger is null, if the cast has been unsuccessful, then we just return this is not a viable threat, it's not in the correct format. Next, what we'll do is we will just cache in a local variable the world space position of our sensor. So I'll say agent sensor position equals zombie state machine dot sensor position. Now we need to measure the distance between our agent sensor position and the source of the threat, which is the collider's transform. But we also need to factor in, much like we do with our sensor position property, we need to factor in that lossy scale, because we know that if a sound emitter has a radius, for example, we know that that radius is going to be affected if anything above it in its own hierarchy has a scale assigned to it. So I think what I'm going to do is, because there may be lots of different cases where we need to take a sphere collider in the world and transform it into a world space position and a world space radius, I think I'm going to create a helper function to do this, and I think I'm going to make it a static member of the AI state base class, so that we can just call it by doing AI state.get sphere collider world position or something like that. And of course, the code itself, if I go back to my AI state machine class, the code itself is going to look very much like this sensor position and this sensor radius property. Almost identical. We're just going to copy it over and make it available so that we can use it to transform any sphere collider into world space when we want to, not just the sensor position of the zombie. So like I said, I'm going to put this, I think, in the AI state class, and this is going to be a static function, okay? So it's going to be a method of the class, not of any particular instance. So this is going to be a public static function, void return type. What this function needs to return really is the world space position and the world space radius of the sphere. So we need to factor both those things into account. So rather than return a single value from the function, we'll pass in two out parameters that the function will be responsible for filling with the position and radius. So I'm going to call this function convert sphere collider to world space. It's a bit of a long function name, isn't it? But hey, at least we know what it is. So as the first parameter, we need to pass in the sphere collider that we actually want to convert. And then we're going to pass two output parameters. So they're going to be, the first one's going to be a vector3, which is going to be the position that will contain the world space position of the sphere collider when the function returns. And as another out parameter, we're going to pass in a float, which is going to contain the radius on function return. Now we've seen before that we're going to get errors if for whatever reason we return without these values set. So let's just set some default values for those, just in case we've been passed an invalid collider. So I'll say pos equals vector3.0 and radius equals 0, like so. And then of course, if the collider is null, then we will return. Not a lot we can do, and we've at least properly fleshed out those two out parameters. So if we get to this next section of the code, then we know we've got a valid sphere collider and it's time to convert it into world space, taking its parent hierarchy scales into account. So the first thing we'll do, and we'll store in pos, is we'll store the actual position of the transform of the sphere collider. So this is the world position of its transform, but remember, this might not be the world position of the actual sphere collider because it may have had its center offset from its transform. So we will say pos equals collider.transform.position. Now we're going to do what we did in the sensor position property of the state machine, where we're going to add on to this position the center offset multiplied by the lossy scale, and we do this on a per component basis. So first of all, we will add on to position.x the collider's center.x component multiplied by the lossy scale of the collider's transform. That's its x component also, because we're doing this on a per component basis. So we need to do this same thing now for the y. So pos.y plus equals the collider's center point dot y component multiplied by the y component of this transform's lossy scale. And then of course we do exactly the same for the z component. And now what we correctly have is the position of this sphere collider in world space. So now we need to do the same for the radius. We need to calculate the radius. Now remember, with our sensor trigger, which is here, in fact I'm probably going to copy this code over because it's going to give me a head start. All we have to do is we have to find out which is the most dominant component of the lossy scale. and use that to scale the local radius by. You remember a few lessons ago we examined what happens to a collider when we scale up its transform non-uniformly, and we saw that the radius is adopted from the most dominant or the most aggressive scaling factor in its transform. So I'm going to copy that over and I'm going to paste that underneath. We're going to get a load of errors to begin with. So we just want to change sensor trigger to the actual collider that we're testing. So we'll change col there, col there, col there, just changing the sensor trigger to the actual collider that we're testing against. So you can see the first thing we do in our radius member is we store whatever is the maximum, the local radius of the collider multiplied by the x component of the lossy scale, or the radius of the collider multiplied by the y component of the lossy scale. So if x was larger, this will be the x. If y is larger, it will be the y. And then we kind of do the same again. We just need to test it against the z component using the same method. So we're going to take whatever our radius is above and take the maximum of that and the collider's radius multiplied by the collider's lossy scale z component. And I think that pretty much does it. Let me just put some comments in here. So at the top here I've said for the comment, it converts the past sphere collider position and radius into world space, taking into account hierarchical scaling. And then above here I'll just say calculate world space position of sphere center, and then here calculate world space radius of sphere, like so. Let me just save that off and check I haven't got any errors. Okay, all's good. So we've got this nice little utility function now, which is a static member of our AI state class that any function can use anywhere in our script if we want to convert a sphere collider to world space. So going back now to our zombie state where we were dealing with the sound emitter, what we can now do is we can now fetch the world space position and radius of the sphere collider by using that function, and then we can then compare that world space position against the sensor position, which of course is the world space position of the center point of the state machine's sensor trigger. So to do that, we need to first of all declare those two variables that we're going to pass in as out parameters to that function we've just created, so that on function return they contain the position and the radius. So I'll create a vector3 called soundPos and a float called soundRadius. And then I will call our AI state convert a sphere collider to world space function, passing in our sound trigger, passing in the sound position and the sound radius variables as out parameters, so that on function return these variables will contain the correct information. Once we have that, we can then calculate the distance. So I calculate distance to threat equals our sound position, which we've just calculated above, the world space position of our emitter, minus the agent's sensor position, dot magnitude. Now obviously this is just another way of saying vector3 dot distance and passing in soundPos and agent sensor position, but sometimes I like to mix it up to show you the many different ways that you can do the same thing. So this is just the same as saying distance vector3 dot distance soundPos comma agent sensor position. So now what we want to do, much like we did up above with the aggravation factor, is we want to calculate a sound factor by dividing this distance by the radius of the sound emitter. So the way to think about this is, although this event has been raised by the sound emitter trigger overlapping the sensor trigger, we know that sensor trigger is pretty big, doesn't necessarily mean that the zombie can hear this sound. In order for the zombie to hear the sound, the zombie itself, or in other words the zombie's head, which is the sensor position, has to be inside to some degree the sound emitter's sphere trigger. So we're only using the overlap between the sensor trigger and the sound emitter trigger to put something in the queue that needs to be examined more closely. But now we've got here and we have the distance to the threat, we need to see if that distance is actually smaller than the radius of the sound emitter. So the first thing we're going to do is we're going to create a kind of distance factor, much like we did up above with the aggravation factor, by dividing the distance to threat by the sound emitter's radius. So whenever the zombie is within inside the sphere trigger, there's going to be a distance factor of between 0 and 1. If that factor is ever larger than 1, then we know that the zombie is further away from the sound than the radius of its trigger. This isn't a threat that we have to consider. So I'm going to create a float. I'm going to call it distance factor, and it's simply the distance to the threat divided by the sound radius. And like I said, provided that the zombie is inside the sound emitter's trigger, then this will be a 0 to 1 range. Really, a lower distance factor means that the zombie is closer to the origin of the sound source. It's becoming closer to the center of the sound emitter. So we could at this point just say that if the distance factor is less than or equal to 1, the zombie is inside the sound emitter's range and he or she can hear it and can react to it. However, I also want to factor in the hearing property of the AI zombie state machine. We have that hearing property that is a value between 0 and 1, which describes the capability of the zombie's hearing, where a value of 1 means the zombie has full hearing range, but a value of 0.25 would mean it only had quarter that hearing capability. So what I'm going to do now is I'm going to bias this distance factor just before we do the check to see if it's larger than 1, and if it is, then we bail. And I'm going to kind of essentially push the threat further away from the center point of the sound emitter as the zombie's hearing capability is diminished. So it's better really just to see what this looks like. So I say distance factor, which remember is a 0 to 1 range value describing the penetration of the zombie sensor position into the sound emitter. But then I'm going to add on to that the distance factor again multiplied by 1 minus the zombie state machine's hearing capability. So in the case where the zombie has full 100% hearing capability, this line is essentially a no-op, and distance factor is simply calculated as above. That's because if hearing was 1, then 1 minus 1 is of course 0, and we're adding on distance factor times 0, which would be 0, and distance factor remains unchanged. However, if the zombie's hearing capability was only 0.25, a quarter of the maximum, then of course 1 minus 0.25 would be 0.75, and we would be adding on to the distance factor 75% of that distance factor again. And this in the case where a zombie with poor hearing is maybe half of the entire radius away, the distance factor would now be pushed above 1. So it's almost like we've pushed the zombie temporarily outside of the sphere trigger. You cannot hear this sound. So all we need to do now is we need to say if the distance factor is larger than 1, then this sound is too far away, and we simply return. So if we get to this point, we know that we have a sound the zombie can hear, but we don't know that this is the sound that is of the highest priority, because we may have already, in a previous call to this function in the given update, found another audio threat that is stored in the parent state machine's audio threat member that has a smaller distance. In other words, a sound that is closer to the zombie and therefore is a more urgent threat. So what we'll say is we'll say only store this threat if the distance to the threat is smaller than the distance of anything we might currently have stored in the state machine's audio threat. Actually, I'll change that to zombie state machine just for consistency. But assuming it's true and the distance to the threat that we're currently processing is smaller than any audio threat we may have stored in a previous call to this function during this update, then we call the zombie state machine's audio threat.set function, passing in the type of the threat as AI target type.audio, passing in of course the collider itself, the position of the collider, and the distance to the threat. Now, I suppose really what I should do there is not pass in the position of the transform, but pass in the position of the center point of the sphere collider, which we've already got. It's just sound pos, isn't it? So I think I'll pass that in instead. Just in case, and there's no reason really why it should be, but just in case you've put a sound emitter in the scene that is, for whatever reason, in a more complex hierarchy and is offset from its center position. So there you go. So that is now the sound emitter threat dealt with. So just to recap, if the collider we've been passed is a sound emitter, we cast to a sphere collider. We get the world space position of the zombie's sensor position, its head if you like. We then get the world space position and radius of the sound emitter. We calculate the distance from the agent to the sound source. And then we calculate the distance factor by dividing the distance to threat by the radius, which gives us a 0 to 1 value describing the penetration really of the zombie itself into the sound emitter trigger. And then what we do is we just bias this by saying that if for whatever reason we have set the zombie's hearing range to less than 1, then we use that as a pushing factor to essentially mock up pushing the zombie further away from the sound source. And once we've done that, if the distance factor is larger than 1, we say it can no longer hear it. We're basically saying it's now outside of the emitter's range. If that's not the case though, we say if the distance to the threat is smaller than any audio threat we've currently stored, then this is definitely the new most potent audio threat, and we set that as the audio threat in the parent state machine, calling its set function. So I think the last piece of code that we have to add in here is the code that deals with if the threat, for lack of a better word, is food, which is a dead body which the zombie can feed on, which is the very lowest priority threat. So once again, the way this is going to work is when we have a dead body on the floor, we're just going to determine when it's dead, and we're just going to place a sphere trigger wherever we want the zombie to feed. So it might be on the neck or on the head or on the stomach or on the legs, but once again it's just more trigger interaction. So the actual body has got nothing to do with it. We could just put a sphere trigger in the level, assign it to the visual aggravator layer, and then tag it as being AI food. And even though there's no object there, the trigger's there, the zombie will see it as food, it will run over, crouch down and start feeding at that point. So once again, it's just a trigger that we can put on any object that will make the zombie think it can feed on it. And of course, we're going to be putting that on dead bodies. So we will say else if other.compare tag is AI food. Now, there's some other comparisons we have to do here in this conditional, because we don't want to make AI food the current threat if we've already got a threat that's stored that is of a higher priority. So we'll say if the collider that we're testing is AI food, and the current visual target is not AI target type dot visual player, in other words, if it's not the player, and if it's not a light source, in other words, the player's light, which we know is flagged as being an AI target type visual light, and this is where we're going to use a member of the AI zombie state machine, if satisfaction is smaller than 0.9. Now, remember I said that satisfaction is much like the hunger of the zombie. So what we're basically saying is if the zombie's tummy is at 90% full up, then we're not going to go and look for food just yet. We're not that interested. We're not that hungry. But as the zombie moves around the level and indulges in combat, there are going to be things eventually that make his sort of satisfaction diminish, so the zombie essentially becomes weaker and more interested in food. So we're basically just saying if this threat is food, and we haven't already stored the player or a light source as the most potent visual threat, and if the zombie's satisfaction is smaller than 90%, in other words, it's hungry, then we want to process this threat. I'm just looking at this, whether, because at the moment this would overlap an audio threat, which it probably shouldn't do. So I probably want to check that the audio threat isn't also set to something other than none. So I'll say, and if zombie state machine dot audio threat dot type equals AI target type none. In other words, if no audio threat has been registered at all, then we will step into this function. So you can see that the food is a very low priority threat. It's the lowest in the food chain. So the first thing we want to do is we want to calculate the distance from our zombie sensor position to the collider. We've done this a million times before. Well, not a million, but distance to threat equals vector3.distance, the position of the threat, and the sensor position. Those are the 2 points we're measuring the distance between. Then, next up, we want to say if distance to threat is smaller than the state machine's current visual threat dot distance. Now remember, this code is only ever going to be stepped into if the visual threat that we've currently got stored is basically AI food or none. We'll never step in here if it's a threat that is of a higher priority, such as the player or the player's flashlight, etc. So if we step into this code, we know that if there is a visual threat, then it's going to be AI food. So we want to go for this AI food if it's closer than any other AI food we've stored. And if it's not, then we just ignore this object of interest. So inside this conditional, we're going to say if the collider is visible. Now this is an important point because we don't want the zombie running to feed on a body that is behind a building, right? Because it wouldn't be able to see that body. So we're going to do the whole, if it's within the field of view and it's got clear line of sight, then the zombie will go and feed on it. So we're going to use our collider is visible function again, passing in once again the collider that we want to test. Also passing in as an out parameter a hit info, just in case we want to get any information back, which I don't think we do in this particular case. And as the third parameter, you know that we pass in the layer mask of the layers that we wish to include in the raycast. Now, when we did this with the player up above here, where is it? There it is, this line here. Put that down like that. You can see that we passed in the player's layer mask. And the player's layer mask was essentially, it contained the player layer, the AI body part layer, and the default layer. Now in this case we want to include these layers and an additional layer. We want to include the visual aggravator layer because the AI food is going to be on the AI aggravator layer, and that's the thing we're casting array to, and hopefully the thing that we're going to intersect if there is clear line of sight. So what we're going to do here is we're going to create another layer mask, and this is just going to be a layer mask that is used when we're establishing line of sight, not with the player, but with any visual threat. So once again, I'll make a protected int. I will call it the visual layer mask, set to -1 by default, and then here I will do a copy and paste, change it to visual layer mask, and we're just going to add another layer in there, which is going to be the visual aggravator layer, like so. And then if we scroll down to our code, I called it the visual raycast mask. I'll just call it the visual layer mask. There you go, like that. So when we call this function, if the zombie has line of sight, then it basically means that this function is going to cast a ray to the food source, and the collider that the ray is going to intersect is going to be the actual food source. So this function will return true, and we know that all we have to do then is set this as the new visual target for the zombie. So we will say zombie state machine visual threat.set, and this time as the target type we pass in AI target type visual underscore food, which is a special member of that enumeration that we've set aside for identifying targets that are of type food. Once again we pass in the collider's position, and the distance to the threat, and that's pretty much now our AI zombie state class done, I believe. We've got all of the basic threat assessment code in there, and in the next lesson what we're going to be doing is we're going to be writing now the individual states that are derived from this class, and it's going to be those states such as the idle state, the patrol state, etc., which is going to be responsible for examining the audio and visual threats that have been compiled each update and deciding what to do about that. You know, if we're in the idle state and we get either an audio threat or a visual threat, then it's probably going to transition out of that state into the pursuit state. But if we're in the idle state, there's nothing happening, and the idle max time is reached, then it may just, gently drop out of the idle state into the patrol state and start patrolling a series of waypoints in its assigned waypoint network. Once again, I will put the modified versions of the scripts up in the resources section so that you can download them, have a look at them. And when I come back in the next lesson, like I said, we're going to start creating the actual states that make the zombie do something. And we're probably going to dedicate a lesson to each state. So once again, this has been Gary Simmons for the Game Institute, and I will see you in the next lesson. Bye bye now.